Welcome to next lesson in AC circuits. Here in this lesson we will discuss another method for the solution of AC circuits. It is called the method using J operator. So J operator and its applications in AC circuits. J operator is mathematically square root of minus 1. It is an imaginary number. It is called J. J is equal to square root of minus 1. You know that square root of a positive number is a real number. For example, root of 9 is plus or minus 3. But square root of a negative number, root of minus 9, it can be written as root of minus 1 into 9. Root of 9 is 3 plus or minus 3 and root of minus 1 is j. So it will be plus or minus 3j. This is also a purely imaginary number. And if you have a number like this, for example 3 plus 4j, out of that 3 is the real number and 4j is the imaginary number. This type of numbers consisting of both real and imaginary part is called a complex number. So in a complex number there will be a real part. Here 3 is the real part, which is a real number, and the coefficient of the number j is, now here it is 4, it is called the imaginary part. Remember, imaginary part is also a real number because 4 is real number, but 4j is imaginary, and 4 is called the imaginary part of the complex number. Now the complex number can be represented graphically by using a diagram called Argand diagram. As j is equal to plus or minus square root of minus 1, j square will be equal to minus 1. That is, j into j will be minus 1. So multiplication of a quantity by j square is equivalent to multiplying it by minus 1. So if we multiply a vector with j square, it is equivalent to reversing the direction of vector, or we can say that rotation by 180 degree. For example, here in this diagram, plus 1 is in this direction. If that plus 1 is multiplied with j 2 times, j into j square, it becomes minus 1. So if a quantity is multiplied with j 2 times, it is a rotation by 180 degree. Thus we can say that multiplication by j once will produce a rotation by 90 degree in the anti-clockwise direction, because anti-clockwise direction is taken as the positive direction. And similarly, multiplication by j by minus j is a rotation by 90 degree in the clockwise direction, that is in this direction, clockwise direction, because clockwise angles are measured as negative. Another important property is 1 by j is equal to j by j square, because multiplying both sides by j, that is equal to j by minus 1, because j square equal to minus 1, so it will be equal to minus j. 1 by j is equal to minus j. Now the Argand diagram is the representation of any complex number in a two-dimensional plane containing a real axis, that will be x-axis, and an imaginary axis, that will be y-axis. This is the real axis and this is the imaginary axis. For example, here it is plus 1. If plus 1 is multiplied by j, you will get 1 into j, that is j. It will be represented here because multiplication by j produces a rotation of 90 degree. So it becomes imaginary axis. If j is again multiplied by another j, it will be j square, it will be minus 1. So it will further rotation of 90 degree. If it is again multiplied by j, it will be minus j, so further rotation of 90 degrees, so total 270 degree. If that minus j is multiplied with j, it is minus j square, that is minus into minus, that is equal to plus 1. So it will produce the original, that is the real axis. And similarly, the multiplication by minus j, if 1 is multiplied by minus j, you will get minus j, so that is a rotation by minus 90 degree. So in short, the physical interpretation of the operator j is multiplication of a quantity by j produce a rotation of 90 degree in the clockwise direction, and multiplication by minus j produces a rotation of 90 degree in the clockwise direction. Multiplication by j produces anti-clockwise direction, and multiplication by minus j produces clockwise direction. Here the Argand diagram contains z is equal to 4 plus 2j. An example is 4 plus 2j. So 4 is the real part and 2 is the imaginary part. So that number can be represented by this one, z equal to 4 plus 2j. In general, any complex number will have a real part x and imaginary part y. Say capital Z equal to x plus jy. Then it can be represented by this. On the x-axis, the length is x. On the y-axis, the length is y. And this, the diagonal will be the complex number z is equal to x plus jy. So the magnitude of that complex number is z is equal to root of x square plus y square, and the magnitude can be represented by small letter. Here there will be an e, there is a small mistake, the magnitude will be small e, and so we can represent the magnitude by small z. The magnitude small z is equal to root of x square plus y square. Here the real part x is equal to z cos theta. If z is taken as the magnitude, that is the length of this complex number, then this x will be the component of z along x-axis, that is z cos theta, and y component, that is the real imaginary part y, will be equal to z sin theta. So the complex number z is equal to z cos theta plus z j into z sin theta, because this is the quantity x plus j y. So that is small z. Small z represents the magnitude of that complex number. Small z into cos theta plus j sin theta, that is capital Z, that is the complex number, is equal to small z, that is magnitude of complex number, into e raised to j theta. Here theta is called the argument of the complex number, and theta will be equal to, tan theta will be equal to y by x. So theta will be equal to tan inverse y by x. That is tan inverse imaginary part by real part. It is called the argument of complex number. So in short, any complex number can be represented as x plus jy. Magnitude is root of x square plus y square, and the phase or argument will be tan inverse y by x. Now application to AC circuits. The voltage across a resistance R in an AC circuit is in phase with current I. So both voltage and current are in the same direction. So we can say E is equal to IR. There is no phase difference between them. Both of them are in phase. So no problem here. But the voltage across N inductor leads the current I by a phase of 90 degree. Magnitude of voltage E is equal to I into XL, which leads the current I by pi by 2. So we can say that voltage E is equal to XL I, and that quantity should lead I by an angle of 90 degrees. So we have to multiply by J. So E will be equal to J XL I, or J omega L into I. Or we can say that the inductive reactance XL is actually a complex reactance. It is equal to J omega L. Here it is J omega L. The magnitude of that inductive reactance is omega L. Similarly, in the case of a capacitor, the voltage lags the current by pi by 2. So in that case, magnitude of voltage is equal to current into capacitive reactance, that is I into Xc, which lags the current by pi by 2. So we can write E is equal to minus J into Xc into I, because this is negative, because E lags I by pi by 2, and minus J is 1 by J. So that can be written as Xc is 1 by omega C minus J by omega C I, or 1 by J omega C I. Or we can say the capacitive reactance is also an imaginary reactance. It is equal to 1 by J omega C. So in short, we can say that resistance is a real quantity. That is in the impedance of AC circuits, resistance part is real capacitive and inductive parts are imaginary. Now in RL series circuit, current I is same through R and L, but the voltage across L plus voltage across R is added to get the total voltage. So the total voltage E is equal to IR plus J omega L into I, because here J will be there because this voltage leads the voltage across the resistance by an angle of pi by 2. So J omega L into I. We can say R plus J omega L into I. So this R plus J omega L is the impedance of LR circuit. It is called the impedance of LR circuit. Magnitude of impedance is equal to root of R square plus omega square L square, and phase difference is equal to phi is equal to tan inverse imaginary part divided by real part, so omega L by R, as given by the previous explanation. Similarly, in the case of RC circuit, E will be equal to IR plus 1 by J omega C into I, that is equal to R minus J by omega C into I, that is R minus J by omega C is the impedance here. Magnitude of impedance is again R square plus 1 by omega C whole square, and phase difference phi is equal to tan inverse minus 1 by omega CR, because there is minus 1 by omega C by R. Here it is negative because E lags the current by an angle of tan inverse omegas 1 by omega CR. Now in the case of LCR circuit, E will be equal to IR plus J omega L into I plus 1 by J omega C into I. So R plus J into omega L minus 1 by omega C I. So E by I is equal to R plus J into omega L minus 1 by omega C. This is called the impedance of LCR circuit. Magnitude of impedance will be R square plus the square of the imaginary part, that is omega L minus 1 by omega C whole square, and the phase difference between E and I will be phi equal to tan inverse omega L minus 1 by omega C by R. So this is the application of J operator into AC circuits. Another example is, for example, if you are asked to find the resonant frequency of the following circuit with R not negligible. We have already discussed this case with R negligible, which was very easy. But if R is not negligible, this is not that much easy, but it will be very easy when we use the J operator. So in the parallel circuit, the admittances are combined. Admittance means it is the reciprocal of impedance. So 1 by R is equal to 1 by R1 plus 1 by R2, that is in the case of DC circuit. Similarly here, 1 by Z is equal to 1 by Z1 plus 1 by Z2. So there is two parallel branches. The total impedance, if Z is the total impedance, then 1 by Z is equal to 1 by Z1, that is impedance of this RL, that is R plus J omega L, because this R and L are in series. So the total impedance of this series circuit will be R plus J omega L plus 1 by the impedance of this capacitance will be 1 by J omega C, that is 1 by J omega C. So that is equal to 1 by J omega C is J omega C, and this R plus J omega L can be multiplied with R minus J omega L in the numerator and denominator. So we get R minus J omega L by R plus J omega L into R minus J omega L becomes R square plus omega square L square. This is multiplied in order to avoid the imaginary quantity from the numerator, from the denominator. Now resonance like resonance phi will be 0, that is phase difference 0. Phase difference 0 means phase difference is tan inverse imaginary part by real part. Phase difference 0 anengil imaginary part of impedance should be 0. Imaginary part of impedance Z is 0 anengil imaginary part of 1 by Z is 0. So if we equate the imaginary part of 1 by Z equal to 0, we will get the frequency f is equal to 1 by 2 pi into root of 1 by LC minus r square by L square. അല്ലെങ്കിൽ angular frequency omega equal to root of 1 by LC minus r square by L square. So from this expression we will get the special case. If r is equal to 0, we get 1 by 2 pi root LC as in the previous case. So this circuit, the solution of this circuit was very easy because of the use of J operator. So J operator can be used for any complex AC circuits, series parallel combinations. So thank you for watching this video.